Okay, welcome back. Our next speaker is Vera Miloslavskaya, who is at the University of New England in Australia. I believe it's earlier than 6 a.m. where she is, so we really appreciate her waking up so early to give this talk.
Thank you for the introduction. So as you can see, my talk is about precoded polar codes with high error correction capability. So first, I will provide some background on polar code, and then we'll focus on polar code design. And we'll treat polar code design as a constraint optimization problem. To solve it, of course, we need to select design criteria, optimization criteria, then find appropriate optimization techniques, and it is desirable to reduce the search space size. So polar codes introduced by Arıkan in 2009 have a simple recursive structure, and they are famous for their ability to approach the channel capacity as the code length goes to infinity, and the simple successive cancellation decoding. However, practical data transmission systems require codes of moderate length. And so frame error rate of polar codes was reduced by using least successive cancellation decoder. And then it was further reduced. So decoding error probability was further reduced by concatenating polar codes with cyclic redundancy check codes. And such polar codes with CRC were adopted in the 5G standard. Future networks, that is beyond 5G networks, 6G networks, require more powerful codes. And promising candidates can be found among precoded polar codes. The class of precoded polar codes generalizes the original polar codes and polar codes with CRC. Among precoded polar codes, it is possible to find such that have a lower decoding error probability because of additional flexibility of this code construction. Originally, they were proposed in 2013 under the name recorded polar codes with dynamic frozen bits. Let us look at those codes from mathematical perspective. So codes are based on kernel, 2 times 2 kernel. Then we can compute m times Kronecker product of this kernel. Here is an example for code length 8. And this matrix is called polarization transformation matrix. To obtain a generator matrix of pure polar code proposed by Arıkan, we need to eliminate some rows, and this can be represented as multiplication of a polarization transformation matrix by precoding matrix. And our frozen set specifies which columns in precoded matrix should be 0. In this particular example, we have a frozen set of cardinality 5, and this cardinality is equal to the code length 8 minus code dimension 3. So all columns corresponding to frozen positions are 0, and in other columns, we have identity matrix here. In the case of precoded polar codes, we copy some part of precoding matrix, like those black zeros and red units. First unit in each row we copy. But then there is some flexibility. Those violet elements can take basically any values, and which values they would take, it is defined by frozen bit expressions. So we have some expression for this frozen bit. It defines those values. And also expression for this frozen bit, number 4. It will define value of this bit. Yeah, and it is desirable to use this additional flexibility to improve frame error rate under least successive cancellation decoding. In the case of a pure polar code design problem consists in finding frozen set. In case of precoded polar codes, we need to find both frozen set and the expressions for frozen bits. An interesting question is how to design polar codes, like pure polar codes and precoded polar codes. To answer to this question, we represent polar code design as a constraint optimization problem. So we want to use optimization criteria that are meaningful and at the same time easy to compute. Then we will find appropriate optimization techniques for such optimization criteria. And we want to reduce search space size so that our solution, our maybe local optimum, would approach global optimum. About state-of-the-art design criteria for polar codes. So, of course, for any particular decoder, we can perform decoding simulations and find frame error rate, and then try to modify codes to reduce frame error rate. However, the computational complexity would be very, very high, prohibitively high sometimes. So it is desirable to use design criteria given by some analytical expressions. So for SCL with list size 1, that is successive cancellation decoder, we have analytical approximation of the frame error rate, and it requires to know only frozen set and bit channel error probabilities. On the other hand, we know that SCL with large list size can approach maximum likelihood performance. And so we are looking at bounds for maximum likelihood decoding. The most widely known bound may be union bound. This type of bounds uses weight distribution. In general, for linear block codes, computation of weight distribution is a very complex problem. However, for polar codes, for some types of polar codes, we have efficient methods. So first, for pure polar codes satisfying partial order constraint, we can compute the exact number of minimum weight code words. Then for some precoded polar codes, we can compute partial weight distribution, that is first components of weight distribution. And there is also quite efficient approximation of weight distribution for polar codes with near uniformly distributed frozen bit expressions. And we are using those techniques. although there is no analytical expression for error probability under ACL decoding, but there are analytical bounds for the average list size required by ACL to approach maximum likelihood performance. And those bounds take as input frozen set and bit channel entropies. And they can be quite easily computed, for example, for AWGN channel. Okay, how we used those criteria in our code design. So for very short codes like length 32 and 64, we can perform joint optimization of frozen set together with frozen bit expression. And this joint optimization is organized in such a way that we find code with the lowest possible successive cancellation decoding error probability and the constraint that minimum distance is large enough. Typically, this large enough means that we took minimum distance from extended BCH codes. In this way, we balance successive cancellation and maximum likelihood decoding error probability. The result is that we have codes with weight distribution similar to extended BCH codes, sometimes a little bit better, sometimes a little bit worse. So, and the advantage compared to extended BCH codes is that we can approach maximum likelihood performance with lower decoding complexity, that is with lower list size. Okay, then if we increase the code length, then we need to impose additional constraints on the code structure to be able to find a near optimal solution. And so we basically sandwich our code because we specify that our code should be a subcode of a preselected one, and also it should be a supercode of another preselected code. In this way, we reduce the search space and then we can find near optimal solution that also minimizes successive cancellation decoding error probability under the constraint provided by minimum distance and some subcode and supercode. For the case of longer codes, joint optimization would not be efficient. It turns out that it is much more efficient for longer codes, focus only on optimization of frozen set and use some fixed expressions for frozen bits. For example, they can be near uniformly distributed using some expression, or there are other techniques to generate frozen bit expressions like in polarization adjusted convolutional codes. So about frozen set optimization. The most popular techniques are some greedy methods. For example, we can construct frozen set element by element, bit by bit, selecting one at a time, or reducing cardinality of frozen set element by element. Another greedy approach is to take one existing very good frozen set and then further improve by modifying one of its elements one at a time. And here we always work with frozen set of the same cardinality. A more general technique, it is use genetic algorithm. They operate not with one frozen set, but with a population of frozen sets, that is with several frozen sets. Those frozen sets gradually evolve using some mutation operation that is applied to each set individually. And then we have operation to combine two frozen sets, and this is called crossover, and also operations to select best frozen set. Okay, even more sophisticated techniques are there, like reinforcement learning techniques. Such techniques are typically used to construct nested frozen sets, which specify not just one code, but a family of codes of all rates. And they can use neural networks to predict frame error rate. However, in the case of reinforcement learning, in the majority of cases, we need a very large data set. And also very large data set is needed in graph neural networks. The main problem, the main drawback for application of all of those techniques, it is a very large search space size. So if we have a code parameter nk, then the total number of frozen sets is n choose k. Of course, a lot of research has been done to reduce to reduce the search space size, that is to impose constraints on the frozen set structure, such that our good codes would be preserved, and at the same time, search space size would be as low as possible. The most widely known constraints are based on the analysis of weights of elements of frozen set. This comes from information about pure polar code. So for pure polar code, for example, to have a minimum distance 8, we know that all indexes of Hamming weight with a binary expansion with Hamming weight, like up to 4 or up to 2 logarithm of 4, they must be frozen. Then there is also partial order. Partial order imposes constraints which are especially valuable for successive cancellation decoder. But if there is some listing decoder, then it is less optimal. And we also have Readmiller codes, extended BCH codes, and other classical codes that can be used to impose constraints on polar code structure. What we propose to do? Actually, we can dramatically reduce the search space size for long codes. So we suggest to parameterize frozen set by just 3 integers. 3 integer parameters that change within moderate range. And then the polar code design problem would be reduced to finding values of just 3 integers. And we can perform optimization relatively easy. For example, in this picture, the optimal solution will be in the top somewhere here, global optimum. And there are some local optima. Nevertheless, the whole surface is relatively smooth. And it turns out that we can find optimal solutions or near optimal just by evaluating just about maybe 50 codes, sometimes 20 codes, or sometimes like 100 codes. This works well for codes of lengths like 1,000, 2,000, 4,000. And codes constructed in this way outperform other state-of-the-art codes for ACL with list size 32, 16,000. And here is picture for codes of length 2,000. Red curve is proposed solution. And 4,000, this one red curve proposed solution. And here are values of those integer parameters found. So they are all relatively similar to each other. Okay, to summarize my talk, I would like to say that we have considered several precoded polar code design criteria intended for code optimization under ACL decoding. And there are analytical bounds which provide opportunity to evaluate codes without performing decoding simulations sometimes. For short length precoded polar codes, it is possible to perform joint optimization of the whole code, that is of frozen set and frozen bit expressions. For long length codes, it appears that the search space size is extremely large, so that it is more efficient to focus only on the frozen set optimization. And further, it also appears that it is good to impose very strict constraint on the frozen set structure to create frozen sets parameterized just by a couple of parameters and then find the optimal values. And this is instead of optimizing a large set consisting of plenty of bits. Okay, thank you for attention. I would be happy to hear your comments and questions.
We have time for a couple of questions.
Mm-hmm. Yes.
So can you use the mic?
Thank you for the nice talk. I'm curious a bit for the simulation results from longer codes. In some sense, what is your feeling about comparisons with other things like LDPC? Do these designs give, with moderate list size like 32, something competitive with LDPC codes of the same length?
Okay, so those codes can outperform LDPC codes. I would say that, as always, the question is in trade-off between the frame error rate and decoding complexity. So, for example, for code of length like 1,000, I have curve for list size 32. Yeah, it is here. And here is curve for list size 16,000. So, of course, if we will take large list size, then we definitely will outperform LDPC codes. Yes, but the question is in decoding complexity, how decoders are implemented, whether we are more interested in the number of arithmetic operations or we are interested in latency. Yeah, so I would say that there are many practical considerations.
Thank you.
So do you sometimes consider an adaptive list size where you start with a certain list size, and if it doesn't work, you increase the list size, or do you mostly focus on either a fixed list size of 32 or 16,000?
Okay. So in results which I provide in this simulation, yeah. So in this presentation, I provided the results for fixed list size, and here we focused on code design for fixed list size. Basically, this is done to simplify comparison with the state of the art. However, for example, I have recently published a paper about adaptive coded polar codes. It is in transactions on communications. So in that paper, we focus on connection between frame error rate and list size. So my opinion that it is desirable to predict code performance for a particular list size before actually performing decoding. And so in our paper about adaptive recorded polar codes, we focused on this problem. Yeah. I understand that most likely your question was about adaptive list size, where we gradually increase the list size starting from lower to higher. Yeah, but I would say that if we think about adaptive decoding that is gradually increasing list size, then this would be more question about decoding, yeah. How to minimize average decoding complexity rather than it is about code design. Sorry, maybe my answer was very long.
Yeah, we have one more question.
Thanks for the talk. I have a question regarding the code construction you mentioned. You try to constrain it on the minimum distance,
Yes.
taking some benchmarks. I wonder if you, when you consider dmin, do you take into account the CRC as the overall code for the, when you calculate dmin, or it's just the polar part? You kind of choose it such that dmin is matching the read molar or EPCH.
Okay, so about those papers, so when we computed minimum distance, we computed it for the whole code. In this notation, we computed minimum distance like for the whole generator matrix given by multiplication of precoding matrix and polarization transformation matrix.
But it's CRC also part of the
and this our code constructions, they have not considered CRC. They considered just general definition of precoded polar codes, and the polar codes with CRC. It can be presented as a special case of precoded polar codes. For example, in case of polar codes with CRC, we will some non-zero elements in the last columns. If we have CRC like 11, then there would be last 11 columns in precoding matrix with non-zero elements. So yeah,
Right,
and we can compute this minimum distance.
Thank Vera again for a nice talk.
Okay, thank you.
So the next talk will be given by Xiao Ma from the Sun Yat-sen University. This is also on short blog.